Welcome to part three. What we're going to do next is talk about multiple input production with calculus. This is where we've been going the whole time. I started with a review of partial derivatives. Now we're actually going to apply them and solve these optimization problems with real production functions and then get the optimal input combinations. So in general, we've seen this problem before. You've got some profit function that depends on both X and Y, fertilizer and seeding rate or something like that. And it's going to be revenue minus cost, which is price times that production function, F of X and Y. So P is the output price times F of X and Y. Then you subtract off the costs for paying for input one, the cost for paying for input two, and then the other fixed costs. We're going to get some first order conditions, one for each variable, and then the second order conditions are going to be a little more complicated. But always remember what your goal is here, is to figure out what the amount of X and Y to use to maximize your net returns. And then you can calculate that X and Y, or you drive that X and Y, calculate yield, you can calculate profits. So our first one here is we're going to set up a story. We're going to say output price is 10, P is 10. Price of X, R sub X, is 2. The price of Y is 3, R sub Y. So how do I maximize my net returns? We're going to have a production function. I've given one here. Just these are all simple integers for your coefficients to make the math a little easier. But price is 10 times the production function. That's the part in parentheses. Then the cost of X is 2 times however much X you buy. Price of Y is 3, so minus 3Y is the cost of Y, and then 8 is our fixed cost. So our first derivative, we've gone through this already, is going to be the price 10 times that derivative of the part in the middle of the parentheses there, the production function. You're going to pick up a 9. Well, let me slow down. The first order condition is going to be for X, and so it's going to be 10 times the derivative of that input, the production function with respect to input X. So it's going to be, you can pick up a 9 from the 9x term when you take the derivative. You can pick up a minus 4x from the minus 2x squared term in the production function. Then you pick up a minus 2y from that cross term of the minus 2xy. So the first derivative is 10 times 9 minus 4x minus 2y. Then you can't forget the price part. The minus 2x gives you a minus 2 when you take the first derivative. So your first order condition there is laid out 10 times 9 minus 4x minus 2y minus 2 equals 0. Do it with respect to y for the second first order condition. It's going to be the 10, but now inside there you can take the derivative with respect to y. You're going to pick up an 8 from the 8y term. You're going to pick up a minus 2y from the minus y squared term. You're going to pick up a minus 2x from the minus 2xy term. And then don't forget the price of y, which in this case is minus 3. And now these are two first order conditions. They're both equal to 0. All we're trying to do is figure out what the X and Y that satisfy both equations. Really, if you really look at these, if you could rearrange them and make them Y equals some function of X for both of them, there are two lines. You're looking for where the two lines intersect. That point is the XY combination. So what I've done here in this slide is just put the two first order conditions at the top again. And we're going to go through the process of solving these two first order conditions for X and for Y. We're going to use what's called the substitution method. Some of you have learned other ways, and that's fine. I'm not going to require any specific way to do it. But what we're going to do here is solve the first equation for X as a function of Y, take that equation, put it in the second equation, the other first order condition, and then solve for Y, and then take that Y, get the number, and plug it in back into the equation you derive for X as a function of Y. You get both X and Y. If you want, then you can take that and put it into the production function, get the Q, and then you can calculate costs and revenues and figure out your net returns. There are other ways to do this as well. You don't have to solve the first one for X. You can solve it for Y. You can solve and then substitute it into this other first order condition. And like I say, you can start with the first or second first order condition and do it that way. There's many different ways to do this. I'm just going to do it this way for this example. So take the first order condition. All I'm doing here is taking the 10, taking the parentheses away, and then combining the numbers. So 10 times 9 is 90, and you got that minus 2, so you get 88. And then 10 times the minus 4x is minus 40x minus 20y. So you get 88 minus 40x minus 20y equals 0. Let's put the minus 40x on the other side and then flip it around. So minus 40x equals 88 minus 20y. And then all you got to do is divide by 40. Then you're going to get x is equal to 2.2 minus 1/2 y. And what do you do with that? Okay, great. All you do is substitute that into the second order condition. So we're going to get x equals 2.2 minus 1/2 y. You can put it into the second first order condition. But before I do that, I'm going to do the same simplification, take away the parentheses, and then simplify it a little bit. So 10 times 8 is 80, and then you get the minus 3, so you get 77. Then you can get 10 times this stuff in the parentheses, so you get minus 20y minus 20x. So 77 minus 20y minus 20x. But what does x equal? X is equal to 2.2 minus 1/2 y. So let's make that substitution here. That's the second row here. So now we've got that part still equal to 0. Now we're going to get rid of those parentheses. So you get 77 minus 20y minus 20 times 2.2 is minus 44. Minus 20 times minus 1/2 is plus 10y equals 0. Now we combine like terms. We got a minus 20y and a plus 10y. You're going to get minus 10y. 77 minus 44 is 33. That's equal to 0. So, or 10y equals 33, or y equals 3.3. Just doing algebra. That's all this is. So then you got your algebra here. You got y equals 33.3, and now we know back up here that x is equal to 2.2 minus 1/2 x, or I'm sorry, 1/2 y. So you just put that in here, and you do the math, and you get x is equal to 0.55. So there, we found the spot where the two lines intersect. And then if you want, you can calculate the output Q that goes with that. You can calculate the costs and the profits, or net returns, whatever you want to call it. But before we go there, we got to talk about the second order condition. Now, in these two input cases, the second order condition gets a lot more complicated. You have to look at the curvature in both the x and the y direction, plus you have this cross direction to make sure you don't have a saddle point where the saddle is curved this way and then this way on the horse, whichever way, forward and back it's curved this way, right and left it's curved this way. There's a spot in the middle where the slope is 0, but it's neither a maximum nor a minimum. Well, first off, you have the same, just like before we had the second derivative with respect to x had to be negative. We have the same thing. The pi sub xx is negative, pi sub yy is negative. But you have this weird cross term, pi xx times pi yy minus pi xy squared has to be positive. Some of you might have seen this. You create a Hessian matrix, the second derivative matrix of all the second derivatives are put into a matrix, and then you take the determinant of that matrix that has to be positive. So pi xx times pi yy down this axis, and then you subtract off pi xy times pi xy. That's the determinant of that 2 by 2 matrix, if that helps you remember it. But anyway, in the way this works, you have to know that that's the second order conditions require pi xx negative, pi yy negative, and pi xx, pi yy minus pi xy squared has to be positive. So in this case here's our first order conditions again at the top, but we're going to take the derivatives of the derivatives. Pi xx is the derivative of the first one with respect to x again. You're going to get the 10 minus 4x, you're going to pick up a minus 40 there. Pi yy, take the second first order condition, take its derivative with respect to y. You're going to get the 10 times the minus 2y, you can pick up minus 20. Then the pi xy is either way you get to it from either equation. You're going to get a minus 2 times the 10, you're going to get minus 20. So now you got the three components, and then you check the condition. Pi xx negative? Yes. Is pi yy negative? Yes. Is pi xx pi yy minus pi xy squared positive? Let's do the math here. You get minus 40 times minus 20. Minus 20 squared is 800 minus 400. It's positive. So therefore, x equals 0.55 and y equals 3.3 as a maximum. So what you can see here is the calculus-based processes are a lot more work. The first one input was much quicker. You could do one pretty fast. The two input case is a lot more two first order conditions. You got to do a lot more work to get the solution to those two first order conditions. Then you got the three parts to the second order condition. It's a lot more work, and there's a lot more ways for things to go wrong. But it's just work. It's just math. Here's a more realistic example. What I've done here is go to an old textbook, Earl Heddy, and I don't know who the Beatty is, or Bide, back in 1983. This is from Real Production Functions. Earl Heddy was a professor in econ at Iowa State and did a lot of work in this production economics way back in the 80s and before that. He was, when I went to graduate school in the 90s at Iowa State, he was already passed. This is towards the end of his career. But it's a milk production function that they derived at the dairy science department there at Iowa State University back in the 80s or late 70s. Have this function here. G is grain in pounds per week. H is hay in pounds per week. And milk production is 25.9 negative plus 2.56 G plus 105 H minus some really small coefficients on the squared terms there. We'll use a milk price of $14 a hundredweight, grain of $3 a hundredweight, and hay of $1.50 per hundredweight. What is the profit maximizing feed ration, grain and hay to use? Well, we'll work this. This is more realistic. First off, go back a slide. Milk is pounds per week. Grain is pounds per week. Hay is pounds per week. These prices are all dollars per hundredweight. And so dollars per hundredweight is dollars per 100 pounds. You have to divide them by 100 to get to the dollars per pound. So $14 a hundredweight for milk is 14 cents a pound. $3 a hundredweight for grain means 3 cents a pound. $1.50 a hundredweight is 0.15, 1.5 cents for hay. So up in this function, you can see it gets pretty messy pretty fast. Lots of big coefficients. 0.14 times that big long production function with its large coefficients minus 0.03 G minus 0.015 H. But everything's still the same. Our first order conditions are going to be price, 0.14, times the derivative of the inside there with respect to grain. So you pick up the 256 from this term. You pick up 2 times that 0.00505 minus, that's where that 0101 minus G. And then you pick up the cross term here, 0.00352 times H. And then outside the parentheses, you pick up the minus 3 cents for the price of grain. Same thing for the hay first order condition, the 14 cents a hundredweight or 14 cents a pound. Then you pick up the derivative of the inside with respect to H. So you get the 105 here. You get 2 times at 0.00109. It's your 00218. And then you pick up that cross term 00352 times G. And the parentheses, you have the 0.015 for the price of hay. If you want, you can just jump right to the optimality condition just to speed things up if you really care about this. If you want to do it this way, you can just set the marginal product of grain equal to the price ratio R for grain divided by P, the price ratio of hay, the marginal product of hay has to equal that price ratio. If you want, again, these are so many different ways to solve these two equations, two unknowns. But I'm choosing this for a couple of reasons. We'll see in a minute. But this is more realistic, and it's very easy to screw up. It's just a bunch of numbers running around and coefficients that are fairly long and lots of zeros in them. And so it's just easy to make mistakes, but we'll work through the process here. It's the same as before. It's the marginal product equal to the price ratio of 214. Now let's solve that first order condition for H. Go through the algebra, put all the G's and H's on one side, then divide by that 0.00352. And what do you get? H equals 666 minus 2.87 G. Take that and put it into the second first order condition and solve for the remaining put that in for everywhere there's an H and then solve for G. So here's the second first order condition. This is the simplified one where I jumped right to the first price ratio, the marginal product equal to the price ratio. And so do the math here. This goes back to the sides. That's where the 943 comes from. Multiply the equation here. There's an H there, so we'll put this equation in for H. That's what goes here. And then the 00352G stays there. Then you just get rid of these parentheses. Again, much more algebra or math. You got to multiply those together and that times that. You get this part of the equation here. It's all equal to 0. Bunch of small numbers. You get 274G minus 0.057 equals 0. Or you can get the G is 0.507 divided by 0.00274 or 185. A lot of math. But this is a much more realistic production function. It's from a real scientific experiment done in the late 70s, early 80s. So 185 pounds of grain. Now you take that G, go back to the other production function or the other equation. H was equal to 666 minus 28.87 G. Put the 185 in there, and you get 135 pounds of hay. Now we check our second order conditions. We'll know they'll pass. I know the price is here, and that one's negative. This one's on the second derivative with respect to H is this really small number, 0.0000305. Here's the cross term, 0.0000493. Then you check here and you get a really small number, 1.88 times 10 to the minus 7th, but it is positive. So we know we have a maximum. So now we can take those numbers. We get something fairly straightforward, 185 pounds of grain, 135 pounds of hay. You plug them in to the production function for milk, and you do the math again. You get 309 pounds a week is how much the cow would produce. Well, that's 309 pounds per week times 52 weeks. If you were able to milk a cow the whole year, it would be 16,000 pounds. That's not very much for today's world. But it's 1983. We just didn't have cows that productive back then. But 16,000 pounds a year, well, 309 pounds a week. Just take the 14 cents a pound times 309, subtract off the price of grain, price of hay times hay, and you get $41.20 a week is what you make per cow. So that's an example. It's much more realistic. It's a lot of work, but you can kind of see the math gets fairly complicated. And the real goal is a couple things. One, learn the principles of doing this optimization. And then two, to figure out how quickly you can get fairly numerically complex with these realistic functions. Take a think break here. Same thing as before. Same production function with all those long coefficients, same prices, but we're going to change the milk price. Instead of 14 cents or a pound or $14 a hundredweight, we'll go with $10 a hundredweight or 10 cents a pound. So price is going to change by a lot. How does the optimal feed ration and optimal output change? So we'll let you work that one through. We'll go through it here in a second, but I would pause and work through this problem. If you got an example worked, sit down and punch this one through on paper, and then you can check your answer here with the think break answer. Okay, welcome to the next part here. I'm going through the think break number 8. You can see the layout is exactly the same. It's 10 cents a pound though instead of 14 cents. So 0.1 times that same long production function, and then 3 cents times G times 1.5 cents times H, both of them with negatives for the cost side. What are the first derivatives? It's the same as before, except now you can have 10 out here instead of the 0.14, or I'm sorry, 0.1 instead of the 0.14. And then this part's still the same. The marginal product inside here is the same. Same thing here. The marginal product inside the parentheses is exactly the same. All that's changed is you get a 10 cents out here instead of 14 cents. And then if you want, I jump to the R over P in marginal price, and so you get the same stuff here. It's the marginal product divided by the price of the marginal product equals to the price divided by the price of milk. And so you can see 3 cents divided by 10 cents is 0.3, and 0.15 cents to 0.15 or 1.5 cents divided by 10 cents is 0.15. So we're going to work through the math the same. We're going to solve that same first order condition, the first one for H. This time it's going to be slightly different, but the numbers are the process is the same, but the numbers are different. And you're going to get H equals 642 minus 2.87 G. You should kind of see how quickly this gets complicated, but the process is the same, straightforward process. It was 666 minus 2.87 G. Now it's 642. Take that, put it into the second first order condition, and you get, do the math here. Here's your second first order condition. Everywhere there's a H, you put in this equation right here, and you get the same process again, just a lot more different numbers. And you get all done, do a lot of algebra, and you get 182.5 pounds per week. And so that's a new solution. We can check the second order conditions. We did it before. It's going to be exactly essentially the same process. Let's plug these numbers in. Well, the second order condition will be satisfied. You can go through the math and show that. But substitute, you get the H, and you get 118 pounds per week, 118.2. And now, how much milk is the process that give you? You go through the math here, and you get 306 pounds per week, which is a little bit less than 309, but your profits are much lower. Instead of $42.20, it's now $23.35 a week. And you have to use that to pay all your costs besides grain and hay for milking these cows. So that's really the purpose was to show you how complicated these can get. But I want to get to this point here, which is a realistic production function and what happens when you make some big price changes. So In this discussion, we'll see the price decreased 29%. It went from $14 a hundredweight to $10 a hundredweight. It's a 29% decrease. That's a big drop. What happened to optimal milk output? It went down 0.9%. It went from 309 pounds per week to 306 pounds per week. Why? Because it was optimal to keep feeding the cow the same amount. You cut back on grain 1.4%, from 185 to 182.5 pounds. Hay decreased 12%, went from 135 to 118, even though it's the cheapest input. You cut back a lot on that one. You cut back not very much on the corn. And what happened to net returns? They went down 43%, from $41.20 to $23.35. The economically optimal response to a large price decrease was a small production decrease and a large profit decrease. That's what I want you to get out of this, is take a real production function, do real prices. What happens is there is a large price decrease for the market price for milk, yet milk production hardly changes at all, but you lose a lot of money. Your profit goes way down. This happens all the time in corn, happens in soybeans, and all the other crops, happens in livestock all the time. The market price changes, but the farmer's response is fairly non-responsive. Output is non-responsive, or what we call inelastic to price changes, but net return is responsive. So here's an example. The supply curve is the same. That's what you're on, but there's been a big price collapse. The demand for milk in this story fell off so that farmers were going, instead of getting $14 a hundredweight, they're getting $10 a hundredweight. The demand shifted backwards, whichever way you want to think of it. So here's the quantity. It hardly changes at all, milk sales, but boy, look at that price. It collapsed from 14 to 12 or 10 cents a hundred, $14 a hundredweight to $10 a hundredweight. Hardly any change in Q. This happens all the time, and we're going to come back to this as sort of several different ways we'll come back to this, but this is a big driver for our economic policy. Think about what happened in COVID. We have a lot of economic policy for agriculture that's trying to deal with this problem right here. Price collapses, and there's very little production change, and income collapses with the collapse in price. Okay, so we're done with this section now. This is the last video, and this is the last of the last video. We've gone through the optimality conditions for multiple inputs. We have several different ways of expressing it, and it's all what we call the equal margin principle. We've done it in theory, we've done it in practice with the table form. We talked about marginal rates, technical substitution, these isoquants, the trade-off curves, and the slope of the isoquant is the marginal rate of technical substitution. Calculated it with delta y over delta x in table, and how to find the optimal input using that. We've also gone into it with using calculus, what we just finished. And then we also talked about different kinds of input substitution. They're the perfect one, like canola and soybean meal in a feed ration, or sorghum and corn maybe in a feed ration. And we talked about imperfect substitutes, which is more typical. And we also talked briefly graphically about perfect complements, which is no substitution. In the end, what you're going to want to be able to do is identify the economically optimal input use in table and in using calculus. So thank you.